All right, let's dive right in. We're going to explore a really fascinating challenge in civil engineering and robotics. And that's how do we create a super accurate digital model of a building as it exists right now? You know, the real thing. It's this whole process of basically reverse engineering our physical world into a smart digital format. It sounds like a huge task, and it is. But AI is totally changing the game for how we manage our buildings. So let's get into the blueprint. It really boils down to this one big question. Think about it. An architect's original blueprint, the as designed model, that's kind of the plan, the theory. But the as built reality, what's actually there, well, that's the ground truth. And trust me, there are always differences. Things change, renovations happen, papers get lost. So, how on earth do we capture what's really there, right down to the millimeter, and turn it into a smart digital file? You know, for the longest time, the only way to do this was just brutal manual labor. I'm talking about teams with measuring tapes and clipboards spending months on a single building. And as a key paper from Tang and his team pointed out way back in 2010, this whole process was, you can imagine, super subjective and full of errors. But now, oh man, technologies like terrestrial laser scanning are completely flipping the script. A job that took months can now be done in just a few hours. We're talking about swapping guesswork for pure data driven precision. And the technology that's making all this happen is called scan to BIM. The BIM part stands for Building Information Modeling. And really, it's all about taking this massive chaotic cloud of 3D data points and turning it into something truly intelligent, an object oriented model. This is what we're talking about when we say high fidelity digital twin. It's not just a picture, it's a smart copy. Okay, so to really get how this works, let's think of it like a high tech detective case. The whole process, from gathering the data to actually doing something with it, it all happens inside what we call a digital twin ecosystem. It's basically the framework for our investigation, this constant loop from the physical world to the digital world, and then back out into the physical world again. So, this ecosystem, this loop has three key parts. First, you've got the sensors. These are our detectives on the ground, things like laser scanners, and their job is to collect all the raw evidence. Then you have the controllers. This is the brains of the operation, the AI algorithms that analyze all those clues. And finally, you have the actuators. These are the agents that act on the findings. It could be a construction robot or even just a dashboard for a building manager. Let's kick things off with the sensors. Our number one detective on the scene is the terrestrial laser scanner. I want you to picture this thing sweeping a room, just firing off lasers and capturing millions, literally millions, of super precise 3D measurements every single second. What you get is something called a point cloud. And every single point has its location, its X, Y, and Z coordinates, but it also usually has color information. It's like we're collecting the geometric fingerprints of the entire space. But, and this is the really critical part, a point cloud on its own is just a bunch of dots. It's basically noise. It's like a ghost of a building, but it has no meaning. The points themselves have no idea that they make up a wall or a door or a pipe. And that is the real challenge for AI engineers. This is where the heavy lifting comes in, interpreting all that data to build a model that actually understands what it's looking at. And that brings us to the brains of the whole operation, the controller. This is our AI detective armed with a whole toolkit of powerful algorithms. We're talking about segmenting, classifying, and figuring out relationships. Honestly, this is where all the scan to be IM magic really happens. And look, this isn't just some black box guesswork. It's a very structured science. Now, yeah, today we often use these big end-to-end deep learning models, but the fundamental logic, the core ideas were actually laid out super clearly in a really important paper back in 2010 by Pingbo Tang and his team at Carnegie Mellon and NIST. They gave us this framework of three core operations, and believe me, they are just as relevant today. Okay, so step one is geometric modeling. The AI detective basically starts sifting through that chaotic cloud of points, looking for basic shapes. It's using algorithms. You might have heard of some like RANSAC to find big clusters of points that look like a flat plane or a cylinder or a sphere. It's the first pass at making sense of the mess. So, okay, the algorithm does its job. It finds a huge flat vertical surface made up of millions of points. Awesome. That's a great first step. But the AI still has no clue what it actually is. Is it a wall, the side of a giant cabinet, a big closed door? To answer that, we have to move on to the next, an absolutely critical step. And that step is object recognition. This is where we go from just pure geometry to actual meaning, to semantics. The AI takes that abstract vertical plane we found and, using machine learning, it gives it a name. It assigns a label. It says, hey, that's not just a plane, that's a wall. Or that cylinder over there, that's a pipe. Now, this is where it gets really interesting because in one of these digital models, a wall or a door isn't just a simple tag. Oh no, it's a really complex data object that has its own kind of digital DNA. And it's all structured in this very specific, very clever hierarchy. So, if you've ever used software like Revit, you'll recognize this structure. It's what makes the model so powerful. So for our door example, you'd start with the broad category, which is, doors. Then you drill down to a specific family, maybe single flush doors. From there, you can define a type, like one that's 30 inches by 80 inches. And finally, you get to the instance, the one specific door that leads to the master bedroom. See? It's incredibly detailed. And that brings us to the final piece of the puzzle, relationship modeling. Because it's not enough to just identify a wall here and a window there. The true intelligence comes when the AI understands how they connect. It needs to know that the window is contained inside the wall or that a pipe goes through the floor. This is about building the whole story, figuring out all the spatial relationships between every single object. Okay, so let's recap. Our sensors have collected all the evidence. Our AI controller has analyzed all the clues. The case is cracked. So, why does all this matter so much? What's the big deal? Well, because once you have this incredibly accurate as built digital twin, you unlock a whole new world of analysis and automation. The possibilities are just huge. For example, you can automatically check if a building meets accessibility codes right against the real world measurements. You can plan a complex renovation and know for sure that everything is going to fit perfectly. You can even use this model to guide robots on a construction site, telling them exactly where to drill a hole or make a weld with incredible precision. It's a total game changer. So, what we have in the end is this really powerful feedback loop. Remember the digital twin ecosystem? We use the sensors to observe the real world. We use the controllers, the AI, to understand it. And then we use actuators to take that digital understanding and turn it back into precise, intelligent action in the physical world. It's a complete circle. And all of this leaves us with a really big, kind of mind blowing question for the future. We've just seen how AI can perfectly understand a building that already exists. So, what's to stop it from designing or maybe even building the next one? If an AI can learn all the rules, all the relationships, couldn't it create something even better? That line between understanding the world and creating a new one, well, it's getting very, very blurry. Thanks for tuning in.